July 9th, 1958, Lituya Bay, Alaska. It is late in the evening, and the remote Alaskan bay is almost completely dark. There are no cities here, no crowded beaches, no warning sirens, only mountains, glaciers, forest, cold water, and a few fishing boats anchored inside the bay. Then the ground begins to move. At approximately 10:15 that night, one of the most powerful earthquakes ever recorded in southeastern Alaska tears through the region. The mountains shake. Rock begins to fall. The water inside Lituya Bay becomes violently disturbed, and at the head of the bay, an enormous section of mountainside is about to collapse into the water. What happens next will leave a scar on the landscape more than half a kilometer above sea level. Trees will be stripped from the mountainside at an elevation of approximately 524 meters. That is roughly 1,719 feet. 3 fishing boats will be caught inside the bay. 4 people will survive. 2 will disappear. And scientists will later discover evidence that the water had climbed higher than almost any tsunami ever documented. But there is an important detail hidden inside the famous 1,720-foot number. This was not a 1,720-foot wall of water traveling through the entire bay. The measurement describes the maximum elevation reached by the water as it surged up the mountainside, and understanding that difference is the key to understanding what really happened. Because the story of Lituya Bay is not simply the story of an enormous tsunami, it is the story of an earthquake turning a mountain into a wave. Lituya Bay lies in southeastern Alaska, along one of the most rugged coastlines on Earth. The region is shaped by glaciers, mountains, earthquakes, and deep coastal inlets. Lituya Bay itself stretches roughly 12 kilometers inland. At its head, the mountains rise dramatically from the water. And beneath this landscape is one of the most important geological structures in the region, the Fairweather Fault. The fault is part of the boundary between the Pacific and North American tectonic plates. The Earth's crust here is constantly being pushed, pulled, and deformed. Earthquakes are not unusual, but earthquakes become especially dangerous when they strike beneath steep, unstable mountains, because once the ground begins to shake, gravity takes over. A mountainside can remain stable for centuries. Then, in a matter of seconds, the forces holding it in place can be overwhelmed. And if that mountainside stands directly beside water, the consequences can travel far beyond the point where the rock falls. Lituya Bay was particularly vulnerable because of its shape. The bay is narrow and steep-sided. At its head, 2 inlets form a T-shaped configuration. One of them is Gilbert Inlet. And it was here, at the head of Gilbert Inlet, that the crucial event of July 9th, 1958 would unfold. A massive rock slide would enter the water. The water would have almost nowhere to go. Instead of spreading freely across an open ocean, the energy would be concentrated inside a confined landscape. And Lituya Bay had already shown that this combination could be dangerous. Long before 1958, enormous waves had struck the bay. Scientists would later identify evidence of earlier giant waves, including events associated with approximately 1936, 1874, and the mid-1850s. The evidence was not preserved in newspapers. It was preserved in the forest. When an enormous wave climbs a mountainside, it can destroy vegetation. Trees disappear below a certain elevation, while trees above it survive. That boundary is called a trim line, and in Lituya Bay, the mountains contained several such signatures. The bay had a history of giant waves. But on the evening of July 9th, 1958, The people inside it had no idea that they were about to become part of that history. Before the earthquake, Lituya Bay was simply a remote Alaskan fishing ground. The water was calm enough for boats to anchor. The surrounding mountains were imposing, but they were part of the normal landscape. Among the fishermen in the bay that evening was Howard Ulrich. He was aboard the fishing boat Idri with his 7-year-old son. Elsewhere in the bay was the Badger, carrying Bill and Vivian Swanson, and another boat, the Sunmore, carried a married couple whose names would later be connected to the tragedy. There was no modern tsunami warning system, no emergency broadcast, no mobile phone alert, no satellite notification, and even if there had been, there would have been very little time to react. The danger was not approaching from hundreds of miles away. It was already surrounding them. The mountains themselves were the danger. At approximately 10:15 or 10:16 p.m., the Earth began to move. The earthquake struck along the Fairweather Fault. Modern estimates generally place its magnitude around 7.8 to 7.9, though some reconstructions run higher. Whatever the exact number, it was enormous. The ground shook violently across southeastern Alaska, and inside Lituya Bay, the effects were even more dramatic. Rockfalls and avalanches broke loose around the bay as the fishermen watched the landscape itself change. Then, at the head of the bay, a massive slope failed. An enormous section of mountainside broke loose near Gilbert Inlet, an estimated 30 million cubic meters of rock, suddenly moving downhill, accelerating toward the water. A landslide entering water does not simply disappear beneath the surface, it displaces it, and the larger and faster the landslide, the greater the displacement. At Lituya Bay, an enormous mass of rock struck the confined water of Gilbert Inlet and generated an immense impulse wave. Part of that energy traveled outward through the bay, but another part was directed straight at the mountainside opposite the slide, and the water began to climb, higher and higher. Trees were stripped away, forest disappeared. The water continued upward until it reached an elevation of approximately 524 meters, about 1,719 feet. That is where the famous number comes from. But this is also where one of the biggest misconceptions about Lituya Bay begins. The wave was not a 1,720-foot vertical wall, traveling through the entire bay. That figure represents maximum run-up, the highest elevation reached by water moving up a slope. A wave can be far lower while still producing an extraordinarily high run-up when it hits steep terrain. At Lituya Bay, the geography transformed the wave's energy into elevation. The mountain became the measuring instrument. The forest became the evidence. While the wave was forming at the head of the bay, 3 fishing boats were inside Lituya Bay, with no idea of the full scale of what was unfolding. They knew only that the earthquake had shaken everything. The mountains were collapsing, and something enormous was moving through the water. Their stories would end very differently. Howard Ulrich and his young son were aboard the Idri. As the mountains moved and rock and ice fell around the bay, the water grew violently disturbed. Then the wave arrived, and the boat rose with it. For a small fishing vessel surrounded by mountains and rapidly moving water, the situation was extraordinarily dangerous. But the Idri survived, and so did Ulrich and his son. Their account would later become a key part of the historical reconstruction. Their survival also shows something remarkable. The water carried enough energy to climb more than half a kilometer up a mountainside, yet a small boat caught inside the bay could still ride it out. Elsewhere, the Badger was carrying Bill and Vivian Swanson. As the wave reached them, it lifted the boat and swept it toward land, carrying it over La Chaussee Spit entirely. The Badger was wrecked, but the Swansons escaped in a small skiff and were rescued. 2 boats had now survived the disaster. The third would not. The Sunmore was also inside the bay. Its occupants tried to escape, but the wave and the violent conditions overwhelmed the vessel. The Sunmore disappeared, and the 2 people aboard were never found. They were the only 2 people who died inside Lituya Bay itself. The earthquake and its landslides caused 5 deaths across the wider region, but only 2 occurred inside the bay, because Lituya Bay was remote, with very few people there. In a densely populated coastal community, an event of this physical scale could have produced a very different toll. After the wave passed, Lituya Bay had been transformed. Forests were stripped from portions of the mountainsides, debris scattered across the landscape. But the destruction also left scientists exactly what they needed: evidence. A line across the mountain showed how high the water had reached. Below it, vegetation was destroyed. Above it, trees remained. The landscape had recorded the event, and the highest point of that record was approximately 524 meters, based not on a dramatic eyewitness estimate, but on physical evidence on the mountainside itself. Geologist Don J. Miller of the U.S. Geological Survey led the investigation, documenting the vegetation destruction, the landslide, and the bay's geography, and comparing the evidence with earlier giant wave deposits and trim lines. His work became one of the foundational studies of Lituya Bay. The question wasn't just what happened, it was how a landslide could create a wave capable of reaching nearly 1,720 feet. There was no camera at Gilbert Inlet in 1958, no instrument recording the rockslide's speed or the first impact. Scientists had to reconstruct the event from whatever evidence survived. Researchers built physical-scale models of the bay, introducing simulated landslides to observe how the water responded, confirming that a sufficiently large, fast-moving slide could produce an enormous wave. Later experiments dug into the physics further. The slide didn't push a clean wall of water forward. It entered violently, accelerating the water, trapping air, with the shape of the inlet and surrounding terrain redirecting the energy. Eventually, researchers turned to computer simulations that reconstruct the underwater shape of the bay, estimate the landslide size and movement, simulate the rock-water interaction, and compare the resulting run-up against what the mountainside actually shows. The goal isn't a spectacular animation. It's testing whether the proposed explanation can reproduce what really happened. Increasingly, the landslide mechanism does. Still, not every detail is settled. The exact velocity and volume of the slide are estimates. How it broke apart entering the water is reconstructed through modeling, and researchers continue debating the precise physics at every stage. That uncertainty isn't a weakness. It's simply what's left when an event happens once and all you have afterward is the evidence. Even the earthquake's magnitude varies by source, commonly cited around 7.8 to 7.9, with some reconstructions as high as 8.3. That doesn't change the central story. The earthquake was powerful enough to destabilize enormous amounts of rock. And critically, the earthquake itself wasn't the wave generator. It triggered the landslide. The landslide displaced the water, and the displaced water created the localized Megatsunami. That's one of Lituya Bay's key scientific lessons. A tsunami doesn't always begin with the seafloor rising or falling. A landslide can generate one too, and when it enters confined water, the results can be extraordinary. The phrase 1,720-foot tsunami sounds almost impossible. It conjures a vertical wall of water towering over the landscape, but that's not what the evidence shows. The figure is maximum run-up, how high the water climbed, not the height of the wave as it traveled through the bay. In fact, away from the impact zone, the wave itself is estimated at roughly 30 meters, about 100 feet, already enormous, but a different thing entirely from 1,720 feet of run-up. The real question isn't, how could a wall of water 1,720 feet tall move through a bay? It's, how could enough energy transfer from a falling mountain into the water to force it more than 1,700 feet up a mountainside? And that's what scientists have spent decades trying to understand. One unsettling discovery came from looking backward. Lituya Bay had experienced giant waves before. Trim lines in the forest point to earlier events around the mid-1850s, 1874, and 1936. July 9, 1958, was not a freak occurrence in an otherwise stable place. The geography of the bay had repeatedly created the conditions for extreme waves. The ingredients were always there: a powerful earthquake to destabilize the slopes, a landslide to enter the water, a bay to concentrate the energy, and mountains to convert that energy into extraordinary run-up. 1958 simply produced the most thoroughly documented example. Those conditions haven't disappeared. Alaska still has steep mountains, glaciers, and active faults, and deep, narrow fjords where landslides can enter water. Around the world, scientists monitor unstable slopes above lakes, fjords, reservoirs, and coastal inlets, because a landslide doesn't need to be enormous by global standards to create a dangerous wave in the right environment. Modern tools, satellite imagery, digital elevation models, high-resolution bathymetry, and computer simulation let researchers study Lituya Bay in ways impossible in 1958. In 2025, NOAA and the National Park Service conducted new high-resolution bathymetric surveys of the bay, giving scientists today a far clearer picture of the underwater terrain than the researchers of 1958, who had only the scars on the land to work with. Think about the three boats again: the Edry, the Badger, the Sunmore, all inside the same bay, facing the same earthquake, the same wave, yet their stories ended differently. Howard Ulrich and his son survived aboard the Edry. Bill and Vivian Swanson survived after the Badger was carried over the spit. The two aboard the Sunmore disappeared. Those outcomes came down to geography, timing, position, and the unpredictable behavior of the water. The people inside the bay couldn't see the rock slide, couldn't calculate the wave, couldn't know where the water would go next. They were inside the event, the measurements, the models, the science. All of that came later. So, what really happened at Lituya Bay on July 9th, 1958? A powerful earthquake struck southeastern Alaska along the Fairweather Fault. The shaking destabilized the steep slopes around Lituya Bay. A massive rock slide broke loose near Gilbert Inlet, tens of millions of cubic meters of rock entering the water, displacing an enormous volume and forming a powerful impulse wave. The confined geography of the bay directed that energy outward, and in the area opposite the slide, the water surged dramatically up the mountainside, reaching, at its highest documented point, approximately 524 meters, about 1,720 feet. The wave stripped trees from the slopes, carried boats, destroyed vegetation, killed 2 people inside the bay, and then it disappeared. What remained was the evidence. More than 60 years later, questions remain. The exact speed of the rockslide, the precise details of its entry into the water, the first seconds of the wave's formation. Scientists can model these processes and test them against the evidence, but every reconstruction has limits, not a weakness of the science, but part of it. Lituya Bay is a historical event that cannot be repeated. Researchers work with what's left behind. Remarkably, that evidence is strong enough to reconstruct the broad sequence with real confidence. Today, Lituya Bay looks peaceful. The water reflects the surrounding mountains, and forest has returned to many of the slopes. From a distance, it's hard to imagine that one of the most extraordinary tsunami events ever documented happened here. But the landscape still remembers. The trees mark where the water reached. The scars mark where the mountain moved. The shape of the bay explains why the wave became so extreme. And the surviving accounts tell us what happened to the people caught inside it.